Okay, what we're going to look at is Chapter 10, Part 1. And so Chapter 10 is about projectile and satellite motion. And what we're going to cover in this first part is we're going to be covering the projectile motion and what that means. Okay, so just pure projectile motion. Okay, so what is a projectile? It's any object that's moving through the air or through space under the influence of gravity. So that's the only force on it. So we're not covering air friction yet. We will talk a little bit about that. And what happens is that objects moving across the Earth's surface through the air tend to make this shape, which is called a parabola. And so this picture is showing a half parabola. So someone who is throwing a stone, that stone will curve down in this gentle shape called the parabola. And here's a skier going through the air, and you can see how the center of mass of the skier is also in this parabolic shape. So yes, anything tossed through the air will follow a parabolic path. Now, parabolic paths result because you have two things going on. In the horizontal direction, you have a constant motion, a constant velocity, because there are no forces on it, right? We said no air friction. So there's no force. Whereas in the vertical direction, there is a force, the force of gravity. So it's accelerating, and accelerating at the rate of g, 10 meters per second squared. Okay, so there is acceleration in one direction, but not the other. And so you can see what's happening here is across the top, we have this red ball, and it's going across at a constant pace in the horizontal direction, but it's gaining speed in the vertical direction. And so those 2 points together give you the location of the ball at each time. So let's say these are 1 second apart. And so at 1 second intervals, here's the ball, and you can see how, of course, it gains speed and distance in the y direction. And so it stretches out the shape into the parabola. Okay, so horizontal constant speed, vertical accelerated. Okay, and so here are just some more drawings, again, showing the constant speed in the horizontal direction, accelerated in the vertical, put them together, and you get this idea of the motions working together. And as the seconds pass by each direction, you would gain distance. But of course, in an accelerated frame, you'll gain more distance per second. So in the y direction, the distance keeps getting greater. Now, there's some interesting things that come from this. For one thing, if you drop a ball, it takes a certain amount of time to fall to the floor. If you project a ball horizontally, it will start falling also. And it will actually fall at the same rate as a ball that was just dropped straight down. So these are actually keeping pace with each other, these balls. And so after 1 second, you can see that they are same after 2 seconds, for instance, this one and this one. After 3, here we've got this one and this one. And so all the way down, they are keeping track of each other. And so the balls would hit at the same time, even though one of them went a greater distance, but that's because it actually had extra velocity in the horizontal direction. So it traveled horizontally, but the motion in the y direction, up and down, the vertical direction, that stayed linked to the idea of the acceleration of gravity. So it takes a certain amount of time to fall, whether it's coming straight down or off to the side. Now, we sort of already talked about this, implied it a little bit when we were talking about conservation of energy, how a roller coaster, you could use that equation, v is equal to square root of 2g delta h, to find the velocity of the roller coaster. But I said that would also could be used for just a falling object. So a frictionless track and a falling object, the time to go down, the velocity for the vertical direction, those would be the same for the falling ball or one going at an angle. Now, you're going to be able to solve problems like this. Here we have a express package plane, and it drops the package accidentally right over your car. Is it going to hit your car? No. Why? Because let's say the plane has a velocity of 200 miles per hour. Well, this package also shared that velocity, right? So the package is not going to hit your car because the package is going to go horizontally as well as vertically. And so it's going to land somewhere over here, not right over your car, because it shares the velocity of the airplane. Okay, so here we have the FedEx airplane drops the crate as it passes over your car. The plane speed is 50 meters per second. And the question is, what will be the place where the crate lands? Okay, so it's coming out of the airplane. And the idea is that we want to find the distance in the horizontal direction from where your car was, okay? So where it was dropped. Now, we do know something already. We know the vertical distance was 200 meters. Okay, so we got that. But what we want to find out is what happens to that package. Where is it going to land? So our unknown is our horizontal distance. Now, when we're doing problems like this, there are certain equations we can use. And we're going to divide it up into horizontal work and vertical work because we have to use different equations. One has acceleration, one doesn't. Okay, so for horizontal, about the only equation we can use really is that distance is velocity times time. That's an equation for a constant velocity. And that's what's going on in the horizontal direction, because we know that the plane and the package are going at 50 meters per second in the horizontal direction. Okay, so we know that, but we don't have the time. So we need to get the time. Where are we going to get that? We're going to get it from the vertical direction. Now, some of the equations you can use in the vertical direction are those equations for falling objects on your equation sheet. There are three possible ones we could use. So one, remember we used to do distance is 1/2 gt squared. That's for a falling object. So we could use that one. We could also use the velocity is equal to g times t. That was one we learned. And then we could use that third one, velocity in the vertical direction is the square root of 2 g delta h. So that would be another one we could use. Okay, all three of those are good for falling objects. So they're good for this vertical displacement. Okay, but let's use the first one because we already know the distance in the vertical direction that it falls. So we know that it is 200 meters. Right, so this is the distance in the vertical direction. This is the velocity in the horizontal direction. And you can use X and Y, of course, if you'd rather. So you can use vertical is Y and horizontal X. Okay, so you can use that too, of course. All right, so we've got 200 meters is that distance, and that's equal to 1/2 gt squared. So 200 is equal to 1/2 of 10 t squared, right, using g as 10. So now what I'm going to do is, of course, divide through, so I get t squared alone. So I'm going to end up with t squared is equal to, you go 2 times 200 is 400, divide by 10, that's going to be 40. And so t is equal to the square root of 40, which is going to be, well, it's going to be like 6 seconds, right? Okay, so let's see if I did the math right. Okay, so square root of 40. Yeah, my calculator needs to be turned on. Is 6.3 seconds. Okay, so that's how long it takes to fall that distance. But while that's going on, remember that the crate was moving horizontally also during those 6.3 seconds. That's what's going to give us our horizontal distance. So that time can come up here, and we can now have the horizontal distance is equal to v of h, which was 50 meters per second, times the time, and the time is going to be the 6.3 seconds. So what are we going to get? We're going to get a distance of 316 meters. Okay, so now we've got a distance that the plane traveled. Okay. All right, so that gives us our distance. Now, some other questions we could ask, we could say, okay, well, what are the final velocities? And well, that's pretty easy to do because we've already got the equations out that we need. We can figure out the final velocities in the vertical distance by using either of these two equations. Since we've already figured out the time, we could go ahead and use this. G times t, that's 10 times the time. So 10 times 6.3 gives us a final velocity of 63 meters per second in the vertical direction. So in the vertical direction, the component of the velocity is 63. Now, what about in the horizontal direction? Well, this is a constant. There's no acceleration in the horizontal direction. So our component in the horizontal direction is going to be 50 meters per second. Now, you're going to be doing a lab like this where there's a ball rolling down a slope, and these gates here are going to measure the velocity of the rolling ball, and then it's going to roll off the table and do projectile motion. And you're going to predict where it's going to land based on that initial velocity. So this will be the horizontal velocity. And the other thing you'll know is how far down it drops. So you'll know the distance in the vertical direction, just like the problem we did. Okay, now when you throw an object up into the air, it has a vertical and a horizontal component to the velocity, usually, unless you throw it straight upwards. And so again, though, these are going to have different things happen to them. In the vertical direction, that velocity is affected by gravity, and so it will get less and less. In the horizontal direction, if we don't count air friction, then that horizontal velocity will be a constant. Okay. So in the vertical direction, it will get less as it goes up, and then it will start coming down and will gain speed. Okay, so here's a projectile that's going upwards, and let's say the vertical is 20, and the horizontal, is 15. So meters per second. After 1 second, the horizontal will still be 15 meters per second, but the vertical would have lost 10 meters per second. So now it's down to 10. After 1 more second, the vertical will now be at 0, but the horizontal component will still be 15. And then as it starts to go down, picking up speed in the vertical direction, then the vertical will be back to 10 meters per second, but now it's going to be negative. The horizontal is still 15, and then it'll get back to the position where it started. Now the horizontal is still 15, but the vertical is now negative 20 meters per second. Okay, so the vertical component changes, the horizontal remains constant. All right, so we saw this picture before. Now, there is an ancient problem in physics, which is called the monkey shoot problem. So the idea is that the veterinarian here, he works for the zoo, and he's got to give shots to this monkey every day who's diabetic. So the problem is to catch the monkey. The monkey doesn't want to get shot. So when he sees the zookeeper and then he sees the zookeeper's finger pull the trigger of the dart gun, he tries to avoid it by falling out of the tree. So you're the zookeeper and you're trying to decide, okay, what should I do? Should I aim directly at the monkey? Should I aim higher than the monkey because I know my bullet is going to curve and fall down? Should I aim somewhere like halfway between? Or should I aim at the ground because that's where the monkey's going to end up? So what should I do? Well, the surprising answer is that you should aim at the monkey, even though you know it's going to fall, because the bullet is also going to fall. So the bullet is going to fall. If the monkey and the bullet are falling at the same rate, then what will happen is that the bullet will strike the monkey wherever it has fallen to. Whereas if you do it towards the middle or something, that will fall too low. It'll be below the monkey. And if you shoot higher up, that won't hit the monkey because it will have fallen. So the thing is that gravity is going to pull the monkey and the bullet downward at the same rate. So yeah, so actually you fire at the monkey. Okay, so anyway, here's a way of looking at that. Here's a cannonball, and one way to look at a parabola is that the cannonball is falling out of its straight line path by a distance. Remember, we got these distances before using d is 1/2 gt squared. So after 1 second, it will have fallen 5 meters. After 2 seconds, it will have fallen 20 meters. And after 3 seconds, it will have fallen 45 meters. And so that's what makes the parabolic path, is that the cannonball here is falling out of a straight line path. Okay, now altitude and range are two things that people are concerned about when they are firing a cannon. And so altitude is how high the cannonball might go. Range is how far. You can think about golf too, right? As a gentler way to think about this. Um, and the thing is, what is the best angle to fire your golf ball, your cannon, to your baseball? Um, well, it turns out that you get the same range from different angles. In an ideal situation without any air friction, it turns out that you would get the same range from 75 degrees as you would from 15. And so the cannonball from 75 and from 15 will hit at the same point. And then you would get the same range if you had 60 degrees and 30. And those will hit at the same point, but a little further along. And the greatest range is given by 45 degrees. Okay, so this is kind of weird, but it turns out that the angles are equal angle on either side of 45. So like 30 is 15 degrees away from 45, and 60 is 15 degrees away from 45, and so on. So they're paired on either side. And the reason for what's going on is that you can be trying for more altitude, so to be higher, or you can try, so here's one trying for more altitude by giving a greater velocity in the vertical direction. At that steeper angle, you do go higher, but you don't have much forward motion left. Your cannon has a total velocity which is limited. So there's not as much forward motion, but you do spend more time in the air. Whereas at a shallow angle, then you have put more velocity into the horizontal speed, but you don't have much time in the air because your ball starts to come down again. Okay, so it is possible for things to be too high, okay, aimed with too much vertical motion, or aimed too low, too much horizontal motion. And so anyway, so that's why they meet when they have certain angles. Okay, but what if it's not an ideal situation? That's for without air friction. But with air friction, what happens is that the range is much less, because the horizontal and the vertical velocities are going to be affected by air friction. And so the actual path, the horizontal velocity is less too. And so you get this much steeper fall here, because you are not going as far per second in the horizontal direction. Anyway, so yeah, so you don't get the maximum range. And it also turns out to depend on the type of ball that you're using. A golf ball has dimples that helps it carry forward. And it turns out that 38 degrees is about the right angle for a golf ball. For a baseball, the baseball has threads on it, the seams, that actually help give it lift also. But even then, you would want the angle to be less than 45 degrees to get the greatest range. Okay, so anyway, so yeah, so air friction makes a difference in the type of the ball in the real world. Now, back in the ideal world, if there's no air resistance, speed going up, speed coming down would be the same. And with air resistance, you would have a little bit of a different height going up, but you still would have the same speed as it comes back down. So, but it would be reduced somewhat. So anyway, so air resistance does make a difference, but otherwise, parabolic motion is beautifully symmetric. What goes up must come down and at the same speed. Okay, and of course fireworks also obey this parabolic idea. Okay, that's the end of this section. We're going to stop this presentation.